Okay, this is Dr. Krause. I promised my students an example of Bode system identification before the midterm, and so this is me doing that. I grabbed this one from last year's midterm. So as I look at this, I see a couple of things. First of all, my slope starts off at positive, or sorry, my phase starts off at positive 90. If I look carefully at this slope, it is a plus 20 dB per decade. So that tells me that I have a pure differentiator in my transfer function. And then somewhere in here, the phase shifts, and it's shifting up, which tells me I have a 0. It seems like it's shifting up by about 90 degrees. If I looked closely, it seems like my phase is changing by plus 20 dB per decade up to 40. So if I drew an asymptote like so, it's a little tricky with that other thing going on there, but it seems like somewhere in that region, which is like 1.5-ish hertz. So it seems like I've got a 0 that's approximately 1.5 times 2 pi is my, and I'm doing this in pen, which is never a good idea. It seems like it has a Z1, or a first order 0 of 1.5 hertz, and then I'm coming along, and if I'm looking at my phase, it drops down 180 back to 0, drops relatively steeply. I see a peak here, and so it seems pretty clear that I've got an omega n that is approximately 100 hertz, so 100 times 2 pi, and I'm going to guess a zeta of something in the neighborhood of 0.1, 0.2-ish. So with that, I think I can say that the form of my transfer function is s plus z1 divided by s squared plus 2 zeta omega n s plus omega n squared. And then maybe I wanted to have an omega n squared in my numerator for scaling purposes and a z1 in my denominator. Otherwise, I could absorb those. Either way, I probably need an overall gain. And so that, with these three numerical values and an estimate for k, would provide me a complete answer. The trick is, how do I find k? And part of what makes that difficult is I can't just plug in s equal to 0, because this whole thing goes to 0 regardless of k, because of the pure differentiator. So I got to pick another point, and I might just come in here and pick 1,000 just because it's nice and flat, and it seems like there's not a lot of margin for error. And so that appears to be maybe 105 dB. And so we have to back out the actual magnitude. So what we're saying there is that the 20 log 10 of g of 1,000 times 2 pi j, so that's the s value that we're talking about, that absolute value log 10, 20 log 10, blah, 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 is equal to 105. So if I divide through by 105 and take 10 to that power, what we're saying is that the magnitude of g j omega, evaluated at omega is equal to 2,000 pi, is equal to 10 to the 105 divided by 20, which works out to be 177,000 something. A big number. I guess maybe not surprising in that this thing does have a differentiator in it. And that's a large frequency. So then the trick would be, I come in here and I plug in s is equal to 2,000 pi j. I've got numeric values for everything except k. I set that equal to 177,828 and solve for k. Thanks.